God, it's so noisy. It's just because I had not talked about the conditioning number when I taught it in the summer. So I'm going to record today's class. So just to add that to the playlist. So, okay. So basically, just to remind you where we were, because, yeah, like unfortunately I was sick last time. Um, so we didn't meet last Thursday, but basically the idea was the following. So, uh, the point is that we were trying to find the polynomial that is kind of like closest, the polynomial of a given degree that's closest to some data points, right? And again, without like going back to what like the definitions on all of these things, the point is that the coefficients that determine the polynomial, if you arrange them as a vector, they need to satisfy this equation, which are called the normal equations, right? So the y vector here was a vector of y values of the data points, and the matrix A was found from the x values of the data points, right? The last thing I was telling you on, I guess it must have been like Tuesday or whenever, is that in most cases, right, this matrix A transpose A, basically it is very realistic to expect it to be invertible. Okay, so in most situations, it's not much of an assumption to assume that this can be inverted. This was called the Gram matrix last time. So if this matrix is invertible, then it's super, like, you can find the solution to this system of equations, and that would determine the coefficients of the polynomial. So that more or less, takes care of how to solve this polynomial regression problem. The only thing I wanted to mention today is a little bit of topics related to kind of like error analysis for this type of problem, because it's a good excuse to talk about the conditioning number of a matrix, which is like a very useful idea just to know about. So I'll kind of like in fact I'll describe it in a slightly more general situation, which is just kind of like um, for systems of linear equations. So it's outside this context. It's just something that you can ask for systems of linear equations in general. Okay, so okay. See something about this. Or I think, or condition number, not conditioning, sorry. Um, and I'm not sure why I was saying conditioning. Okay, so just to make it again kind of context independent, let me start. Like, actually, I'll start with this example. Okay. Well, so let's say you have like a system of equations. So here's the setup. You have bx equals y. So usually the matrix is typically called A, but I don't want to call it A so that you don't think that it's related to the matrix A that I have been using before for this polynomial regression problem. So this is like a completely general problem of linear algebra. So um, you have the system of equations, and if the matrix were invertible, right? If B could be inverted, so like in particular, it has to be squared for that. Squared for that. If B can be inverted, then the solution to the equations, to the system of equations, is just V inverse times Y, right? And that is the solution. And in a sense, that is the end of the story. But in practice, what happens, right, is that you know you kind of like as in anything in numerical analysis, you want to understand the situation of what happens if the values of any of either the matrix or one of the vectors were not known precisely, and there's some errors in the measurements. So what we want to kind of like discuss today is that what happens if you don't know some of like the entries of the vector with exact precision, with exact accuracy, which is kind of like the case in general. First, because if it's experimental data, there will be errors in the measurements. Even if it's just like numeric, like exact mathematical data, once you start on a computer, like there's this floating point arithmetic, there might be some rounding. So like the numbers are never going to be quite like 100% correct. So what we want to study today is uh, how sensitive the solution to the system of equations is to changes in some of the data. And okay, again, just to be a bit more concrete, and then I'll get into, kind of like giving you some definitions. So imagine that let's say that the matrix had been like the system of equations had been the following. So oops, sorry about that. Okay, let's say that this is the system of equations you're trying to solve. Well, I mean, this is easy to solve by hand because it's like a 2 by 2 matrix or whatever. So it's not hard to check that a solution to this system of equations is just 1, 1. So you can check solves this. Okay. Now, what I'm going to do is I'm going to keep the same matrix, but I'm going to make a slight change in one of the values of this vector. Okay. So now what I'm going to I'll put in a different color, the one that I changed. Now we have 1 times x1, x2. I'll change the second number to, instead of being 2.001, it's going to be 2.002. Okay, so it is a very small value in one of the entries, right? I mean, it seems small to us. I mean, that seems reasonable to think that you haven't changed much, right? If you were to solve the system of equations now, I mean, again, like all of this can be checked, but then you find that so now the vector that solves the system of equations is 0, 2. So in the first situation, the vector was 1, 1. And in this second situation, the vector was 0, 2. Okay, which does feel like a big change, from we made a small change in one of these coefficients, right? What, like by 1,000? Like just from 2.001 to 2.002, right? But going from 1, 1 to 0, 2 kind of like feels a lot much more of a change than maybe what you would have expected. Like if you have no expectation, of course, like maybe you don't have any expectations about this, but I mean, it does seem like, oh, okay, something interesting happened here because, this did seem like a somewhat larger change than maybe what you would have guessed. Of course, kind of what is lurking in the back, at least in this case, right? is that if you look at this matrix, its determinant is almost zero, right? Like because like the entries are all very similar to one another. So if you remember, I don't know, well, there is a formula for the inverse of a matrix which involves one over the determinant of the matrix. So these these kind of like having like a big change, it seems plausible that it's related to the fact that this matrix is close to almost not being invertible, and that is true, but still, the condition number of the matrix is a slightly more precise way to make this more clear. Okay, so, but kind of like as a provisional explanation for this change. So the solutions change more than expected, but a provisional explanation is that the determinant of this matrix is close to zero, which means that the matrix is almost not invertible. Okay. But again, the condition number of the matrix will make some of those ideas a bit more precise. Okay, so for that, it is convenient to have a definition of what the norm of a matrix is. So as you may know, when you have a vector, you can find its length or magnitude. That also goes under a different name, which is called the norm of the vector. So norm, length, and magnitude, they're kind of like all synonyms of one another. So let me just say that here. So if the vector, has n entries, v1, v2, up to vn, it's Euclidean norm, which is how this is called, or Euclidean magnitude or Euclidean length. Again, this is the only one I'm going to discuss in this class. I'm not going to put like a lot of like extra specifications, but it's just like the one that is provided by Pythagoras theorem. Okay. So that's what the Euclidean length of the vector is. It's just that again, it goes under the name magnitude or norm. Now, when you have a matrix, there are ways to kind of like define the length of a matrix or like the magnitude of a matrix, in fact, and there are actually many possibilities to do this. Um, but I'm going to use one that's kind of like convenient for our purposes. So I'm going to tell you a possible option for defining the norm or magnitude of a matrix. So I'm going to now I will define an analog of this formula for a matrix. Okay. Um, so this is going to be called the matrix norm. So this is going to be called the matrix norm. And again, I'm calling my matrix B for today, just so that you don't think it has anything to do with the matrix A from previous classes. So this can be applied in complete generality. I'm going to put like two absolute values around it because that's kind of like a traditional notation for a norm. And also to distinguish it a little bit more from the length of a vector, so like that you know that I'm talking about a matrix in this case. So what the matrix norm, one way to define it, which is a little bit abstract, but you'll see it can be made more concrete in a moment, is that okay? So what are matrices useful for? They're useful to multiply them with vectors. So if you have a matrix, it's waiting to be multiplied by a vector. So basically what I'll do is I'll multiply the matrix by a vector. Okay. So a matrix times a vector that gives me a vector. So I'll find its length. Okay, so that's what this means. It means you multiply the matrix with a vector, you take the length of that, then you divide it by the length of the vector v that you started. Okay, so this is kind of like a ratio of two lengths, right? This is a ratio of two lengths, and then the matrix norm, the way you find this ratio for every vector. You find this ratio for every vector, um, and you take the maximum of the number that you get. So this is a maximum. Uh, well, actually, yeah. Let me write it this way. It's kind of like a maximum of a function. So like what I'm saying is that you're going to find the max of this function, which I'm going to call f of v. Let's say that the matrix is m by n matrix. So if you have an m by n matrix, you have to multiply with a vector in Rn, right? So this is kind of like a function, like, of multivariable calculus. Like it's a function that depends on multiple entries, but it's a function of the vector. So this function is going to be this ratio that I was, well, it cannot be zero because you do have to divide by, except the zero vector. I'll write it down for like this matrix I have been working with to make it a little bit more concrete so that you see it's not like a crazy thing. But essentially it says for every vector that's not the zero vector, you multiply by the matrix, you find its length, you divide it by the length of the original vector that has a max, and the max of that quantity, that's going to be the matrix term. It's a little bit of like an odd definition, but you'll see actually it has like some useful interpretations, which I'll mention in a moment. But you should think about it kind of like as a largest possible ratio, of so it is like the maximum ratio possible because this is like a ratio of two numbers. So this matrix norm. Okay. So let me show you how this looks like more concretely. Well, actually, let me do it for a matrix that's a little bit more interesting so that you don't think it has to be square or anything like that. So let's say the matrix had been what it could be 3 by 2. Okay, so here's an example. Two, -1, 1, 1, 3, 4. Okay, let's say that's my matrix P, right? So what I'm saying is that you take a vector. So this is a 3 by 2 matrix, right? You take a vector in R2. So you take a vector in R2. So I'll write V as V1, V2. The only restriction that I have is that this vector cannot be the zero vector. That's the only condition, that you cannot have both of its entries simultaneously zero. So V is not 0, 0. So if you do, so basically what I'm saying is that you look at this ratio of, oops, sorry about that. You look at this ratio of b times the vector v divided by the length of the vector. So what is that? Okay, when you multiply this matrix by this vector, you get, let's see if we can do that. That would be a vector in R3, right? So it would give you 2v1 minus v2. It gives you v1 plus v2, and it gives you 3v1 plus 4v2. That's the vector itself. And the length of the vector v is just Pythagoras theorem, right? So it's like the square root of v1 squared plus v2 squared, right? And this is a vector in R3, so you can take its Euclidean norm or Euclidean magnitude. So it's just like Pythagoras theorem, but applied to this vector in R3. I'll write some problems about this matrix norm so that you can take a look at them over the spring break. If because there are some interesting things here, that you can like study. Okay. So that is a ratio, right, of the lengths. And all that I'm saying is that this is a function of calc 3, right? Like this, I mean, if I had called this x and y, this is literally like a function of calc 3, right? Like it's a function of two variables. Like the two variables are just here, v1 and v2. So I'm just saying like you could try to find its max. I will tell you in a moment why there's always a max. Like this always will have a maximum, an absolute maximum actually. And whatever the absolute maximum is, that's called the matrix norm. Okay. So that is the definition of so basically what I'm saying is that you would find the maximum, you find the maximum value of this ratio, you find the maximum value this ratio takes, and that is precisely the matrix norm. Is that okay? So far, so good, making sense. How are we doing? Okay, so the reason why does this quantity always have like a maximum? So let me just say that. So here's like a question. Why does the maximum well, I guess I don't need the brackets, Well, maybe I'll I'm taking the maximum of this expression. Why does this exist? Again, here the only restriction is that v is not the zero vector. Why does this expression always achieve a max, an absolute max? So there is a property of like the magnitudes or like the lengths, which is that they kind of like behave nicely when you have a scalar. So just like there's like this property. That if you have a vector times lambda, where lambda is a scalar factor, like a scalar, you can kind of like take it out of the absolute value of the magnitude, and it comes out as it just comes out in absolute value, right? So when you have a number times a vector, and if you take its Euclidean length, you can kind of like pull out if lambda is positive, because that's the only thing I need, like, so I'll put it for the lambda positive case. If lambda is positive, this is just, so for lambda positive, a vector times lambda, the length of a vector times lambda is just lambda times that vector. Okay, is that making sense? Now, this quantity, this number, right? So now you just have to play a little bit with the expression. So what is this? How can I use this in this case? Well, first, just to make it a little bit better, this is just like aesthetics because this is like a fraction. You can of course like move the denominator as 1/that. But if you write it this way, this looks like lambda. So let's call this lambda. So I'll call this lambda for now. Okay, I'm calling. It has no relation with eigenvalues, by the way. It's just like scalars. Sometimes I call lambda. Okay, but now I will use a property that I just mentioned where you can reinsert a scalar into the length. So I'll move the scalar kind of like back into the absolute value or back into the magnitude. Okay. So far, so good. But then lambda is a scalar and the matrix is linear. What a matrix being linear means is that you can move in and out the scalars. It's kind of like derivatives or integrals, right? Like the constants come in and out at will. So you can kind of like actually put the lambda next to v. So that's what a matrix being a linear transformation means, or like lambda times v. Right? But what is lambda times b? Now let's use back the definition of lambda, which is 1 over the length of b. So this gives you the b times v over its length, right? Okay, so it's b times this thing. Let me put this in parentheses, actually. Just to make it a little bit more clear. But what can you say about what can you say about a vector divided by its length? They had a name.
No, that's not.
It had a name that starts with the letter U. A unit vector, yeah. So this vector has length 1. What is a vector that has length 1? For example, okay. So this is going to be a unit vector. So this is always a unit vector. Okay. So what can you say about a vector that has length 1? For example, in 2 dimensions, right? In 2D, what is a unit vector? A unit vector is literally a vector whose head or tip, right, is on the unit circle. A unit vector lives on the unit circle. Oops, sorry about that. So this is like the unit circle, like x squared plus y squared equals 1. And for example, in 3 dimensions, what is a unit vector? A unit vector is a vector that lives in the unit sphere. Okay. So that would be a vector on the unit sphere. Oh, sorry about that. Sometimes this app is crazy. So this is like the unit sphere. So in general, what I want you to notice about this is that actually this maximum is taking place on, okay, there's a terminology for this. These sets are called compact, but they're also called closed and bounded. So those are like the ones for where if you remember in Calc 3, I mean, you may mostly, or let's say in Calc 1, where were the problems in Calc 1 where you find the absolute max and mean of a function on a closed interval, right? In Calc 3, those problems become kind of like, oh, maybe you had like a closed triangle or something like that. That's where you try to find the max or mean of a absolute max and mean of a function. In Calc3, the condition for the max to exist was that the region was kind of like bounded, which means it's kind of like a finite size, and then it's closed, which means it's defined by strict either equalities or inequalities with a less or equal to. So these sets, are compact again, which is just like a technical term, and that just means that there's an absolute max and an absolute mean because they're kind of like finite. So that is the reason why um there will be an absolute max because you're finding the absolute max on a compact subset, which is another way of saying a function defined on the unit circle or the unit sphere, etc., will achieve an absolute max and an absolute mean, in fact, but we care about the absolute max. Since those sets or those regions are compact, and compact means closed and bounded. So more precisely, what I'm saying is that another way to think about this norm, this matrix norm, this is like the first concrete thing that I have said. Instead of thinking about it as a ratio of these two quantities, if you want, you can think about it as a max that's taking place on the unit hypersphere. So like this is like the generalization of the unit sphere, or over the unit vectors, like the max is taking place on the vectors of length 1. And if the vector has length 1, then you don't need the denominator, right? Because the denominator is automatically 1. So and the zero vector never has length 1, so that also takes care of the issue of like having to make a remark that you cannot have the zero length. Okay, so this is actually another useful way. This is another useful way of like thinking about the vector, the matrix norm. Both are convenient depending on what you want it for. So, like, it's useful to know both formulas for the matrix norm. Now, what is really cool is that it can actually be computed in terms of like the eigenvalues of a matrix. And now that's where things get interesting. So, okay, so this definition of the matrix norm, what's interesting. Has anyone heard before the singular value decomposition of a matrix? Does that ring a bell? Well, I'll tell you what it is. It's really cool. So what is interesting is that this formula is related to the eigenvalues of a matrix. In fact, like which will be called the singular values. We call the singular values. But before doing that, in that case, I'll do it. Since like the SVD, that's how it's called, like singular value decomposition. It's kind of like a generalization of the fact that matrix of like what happens if you can diagonalize a matrix. It's kind of like the most general version of that. Like what can you do if the matrix is not diagonalizable? Like, so you can do an SVD decomposition. But let me explain it first in the case that the matrix is symmetric. So let's say that the matrix B had been symmetric, okay? So let's suppose, for starters, suppose that B was a symmetric matrix. So B being symmetric just meant that B equals its transpose, right? By the way, anyone feel free to stop me if there's anything that I need to stop, spend more time on the linear algebra stuff, because, I know in differential equations you cover some of it, but if you haven't taken linear algebra, like some of these things may not or not may have been discussed. But if B is symmetric, one of the nice things that happens when the matrix is symmetric is first, all its eigenvalues are real. So it only has real eigenvalues. And the other thing that's super nice is that the eigenvectors, which correspond to these eigenvalues, you can take them to be orthonormal. So you can find a base, like how you would say this is that you can find a basis of eigenvectors which are like a basis for the vector space, which are orthonormal eigenvectors. So let's say this is like n by n matrix. If this is an n by n matrix, you can find n eigenvectors which are orthonormal. So orthonormal just meant that each one has length 1 and they're mutually perpendicular. So you can find n eigenvectors which are orthonormal. Like the orthogonality is really the important condition because once they are mutually perpendicular, you can always divide by their length and that makes them of length 1. So like having length 1 is not such a big thing because you can kind of like always do that. You just rescale any vector by its length and you get a unit vector. What makes it important here is that the eigenvectors are mutually perpendicular. Okay. So that means that their dot product, right, is 0 if like you have two eigenvectors of the matrix. Okay. Now, why is that useful? Again, like if you have seen this before, that's great. If not, I'm just going to tell you what happens. But what happens in this case is that because the vectors are an orthonormal basis, every vector can be written as a linear combination of the eigenvectors, right? So any vector v is a linear combination of the eigenvectors. So you can express any vector as a sum from I equals 1 to n of some coefficients times the eigenvectors, which I'm calling the eigenvectors vi. Okay. Is that okay so far? So good, making sense. Now, for the matrix norm, we can use the second version if you want. For the matrix norm, we have to multiply the vector by the matrix B. So that's a nice thing that's easy to do if you have it written as a linear combination of the eigenvectors, because the way that matrix multiplication works, because it's a linear operation, you can just multiply, kind of like it distributes right over the sum, the multiplication. So really, you just have to multiply the matrix B by each of the eigenvectors, right? But what is the matrix B on a particular eigenvector? That's lambda I times bi, because that's the definition of an eigenvector. That an eigenvector is a matrix of a matrix is a vector for which B times the matrix times the vector gives you lambda I times that vector. So these would give you. Is that okay? Is that making sense? And then, okay. And then for the matrix norm, okay, let me continue here. Let's go to the next page. So for the matrix norm, again, if you want, you can write the matrix norm as a max over the unit vectors, right? It's a max of the unit vectors of the matrix times the vector B, right? But we have this formula for the matrix times any vector B. And so what is the length of that vector? Okay, so let's think about that. So the length of the matrix times the vector is the length of this sum Okay. But that's another nice thing. Once because the vectors are mutually perpendicular, right? This is kind of like, this is similar to, what if I asked you, just like as an analogy, maybe let me put it here. What would you, if I ask you to find the length of 2i plus 3j minus k, right? Well, you would say, oh, that's just Pythagoras theorem, right? So you would just say the square root of 2 squared plus 3 squared plus minus 1 squared, right? The reason why you can do that is because ij and k are mutually perpendicular. So the fact that they're mutually perpendicular is what allows you just the fact that you can just square each entry individually. So essentially, because the vectors vi are mutually perpendicular and each has length 1, they are more or less like a version of ij and k. They are similar like to ij and k. So you can basically apply Pythagoras theorem. So this is just like the square root of the sums of like the squares of each entry. So it's kind of like a version of Pythagoras. And again, that can work only because um that works precisely because the vectors are all orthonormal. But if you apply Pythagoras theorem, you get the sum of I equals 1 to n of ci squared lambda I squared. Is that okay? Is that making sense? Okay. Now, we can say a little bit more about this because okay, so what else can we say here? So the thing is that I didn't write this before, but maybe let me put it here because this is also Pythagoras theorem. The length of B is just the square root of the sums of the ci's squares. So again, that's just Pythagoras. It's a version of Pythagoras theorem because again, these eigenvectors are orthonormal. So essentially, you can find the length in exactly the same way as you would have done if those had been ij and k. That's the advantage of having an orthonormal basis. So if this happens to be 1, if the length of the vector happens to be 1, that means that 1 has to be no. So if the vector is a unit vector, if the length of the vector is 1, so you get that 1 is the square root of this quantity. And then you square both sides just to kind of like get rid of the square root, which is kind of like annoying. And then you get that 1 is the sum of I equals 1 to n of ci squared. Okay. So all these coefficients ci, their squares have to add up to 1 because that's the equation of a sphere or like a unit sphere, right? Like what is the equation of a circle like a sphere? That the sums of the squares equals 1. So that's another way of saying that you're dealing with a unit vector. Now, why is that useful? Because in particular, that tells you that each coefficient must be between -1 and 1, right? The only way for the squares to add up to 1 is that if each of them individually is less or equal to 1. So for sure, that already allows you to say that each ci is between -1 and 1. Okay? Like the only thing I need is for them to be less or equal to 1. So each of these has to be less or equal to 1. So how is that useful? in this inequality. So this length, right? This length, which was equal to the square root, would be equal, less or equal to what I get if I replace each coefficient squared with 1. Okay? But what is that? That is the square root. That is the square root of the sum of the squares of the eigenvalues, right? Actually, let's see. Actually, let me like if I mean this is true, but actually this is too much of an too sharp. So actually, let me. Yeah. It's correct, but it is too much of an inequality. You know, like okay. So I will do this different way. Each eigenvalue, right? These are all the. Let's start with the lambdas. Actually, that's better. Each eigenvalue, the matrix will have a finite number of eigenvalues. If it's like a square matrix, if it's a 3 by 3 matrix, it can have up to 3 eigenvalues. If it's like a 10 by 10 matrix, it can have up to 10 eigenvalues. So there will be an eigenvalue that's the largest of all of these. So I'll call that lambda max. So lambda max. Well, how should I say this? Because the eigenvalues, um, like I mean, the eigenvalues could also be negative, but so you look at them in absolute value. And yes, like let me write it like this because this is going to. Okay, so before I continue, actually, let me write it like this. So define this thing. So it's going to be the maximum of the eigenvalues, but in absolute value, So like the maximum of the first eigenvalue in absolute value, of the second eigenvalue in absolute value, in case some of them were negative, of the third eigenvalue in absolute value, and the nth eigenvalue in absolute value. So here I'm writing it as if the matrix had n distinct eigenvalues, but some of these could be repeated. So that's fine. Like, if the algebraic multiplicity is larger than 1, that's okay. So I'm overcounting them maybe. But once you do that, do it in that way, then each eigenvalue is going in absolute value, like each of them is going to be less or equal to you know each eigenvalue squared is going to be less or equal to sigma max squared. That's why I wanted to write it this way. Okay. And that is the inequality that I'm going to use here. Okay. So just continuing with Pythagoras. So this was kind of like a bit of an aside. By the way, this sigma is called like a singular value. That's why I'm using this notation, because this is the notation for the singular values of a matrix. I'll tell you more about that in a moment. But so if you continue here, this is less or equal to the sum of I equals 1 to n of ci squared times sigma max squared. But the nice thing here is that now this is a constant, doesn't depend on the index because it's the largest value possible. So you can take it out of the sum because it's the same term present on each factor. You can take it out of the sum and then you can take it out of the square root. So it comes out of the square root as sigma max. But what is this? This is just the length of the vector v which was 1 because it was a unit vector. So this was a unit vector, and now this is fine. Yeah, that's like the inequality that I wanted. So this is going to be 1 since V had length 1. So in fact, that what we just showed is that if the matrix had been symmetric, let's just put this all, let me summarize the situation because like there were many things happening here. So just to summarize this, if the matrix B is symmetric, then its matrix norm coincides with this thing that I'm calling sigma max, which is the maximum of the eigenvalues of the matrix in absolute value. So the matrix norm in the symmetric case is the largest eigenvalue in absolute value. Okay, you look at all the eigenvalues of the matrix, take its absolute value, pick out the largest one, and that is the matrix norm in the symmetric case. Okay, in the symmetric case. So that's like a very concrete definition. Like that is a very concrete way to think about the matrix norm. It is just the largest eigenvalue. I mean, again, if you ignore the absolute value because it's kind of like annoying to think about the absolute value part. But what is an eigenvalue? If you think about an eigenvalue or like an eigenvector, that is kind of like the point of an eigenvalue and eigenvector is that when the matrix is an eigenvector is kind of like a direction in space that doesn't get affected by the matrix, it just gets rescaled. So in a sense, this matrix norm is kind of like the largest rescaling factor that the matrix produces on the space because like the matrix, the point of a matrix is that it kind of like stretches out like a space in different dimensions. Like an easy example of that, maybe just to make it more concrete, like if the matrix had been, here's an example, a super dumb example because it's like a diagonal matrix, right? But if the matrix had been 2, 0, 0, 3, okay, in this super clear, like the matrix is symmetric and diagonal, so it's like eigenvalues are just like the diagonal entries, right? So here lambda 1 is 2, lambda 2 is 3, right? And then this sigma max would be 3, right? So what I'm saying is that 3, the matrix norm, would be the stretching factor, the largest stretching factor, because what happens, one way to think about this is that when if you have the unit circle, if you have the unit circle on the xy plane, the unit circle is determined by the vectors e1 and e2, right? But if you apply the matrix B to this picture, then E1 gets rescaled by 2, so it becomes twice as large, and E3 becomes 3 times as large, so the circle becomes an ellipse. So if you kind of like apply, it's kind of like a transformation to the space. So if you multiply each of these directions by the matrix B, actually you end up getting something like this. Where now this is 2E1 and this vector is 3E2. So essentially that's what happens in general when you have a symmetric matrix and you have like a unit circle, it gets you have a unit circle under the matrix, it becomes an ellipse. And then kind of like the point is that the matrix norm is kind of like the largest semi-axis of the ellipse. It's kind of like the largest stretching factor. An ellipse has 2 semi-axes. So like the largest one is kind of like the matrix, or half of it is like the matrix norm. Maybe just to finish it very soon, because that way I can give you back the exams. And well, the only thing I was going to say is that in general, and then next time we can wrap this up. And the condition number is not too hard. Like what was hard is just to get into what is the definition of a matrix norm. But that's an important idea. So if the matrix is not symmetric, this is still useful to know. So what can you do if the matrix is not symmetric? Well, remember, this is actually something we discussed already with the polynomial regression problem. If you have a matrix which is not symmetric, there is kind of like a cousin to that matrix which is always symmetric, which is the Gram matrix. So if the matrix is not symmetric, you have this Gram matrix which was did I define it as B? Let me see where I put which one of these two I put as BB transpose. Where are you? But previous notes. Okay, it was with the transpose on the first factor. So this is always for free a symmetric matrix. Okay, so this is automatically symmetric. And we talked about this last time. It has non-negative eigenvalues. This matrix does have non-negative eigenvalues, and all eigenvalues are non-negative. Okay. So in this case, and kind of like the thing that's miraculous is that this matrix B transpose B has the same eigenvalues as B transpose, which is not clear at all. So like the miracle, and that's actually how singular value decomposition starts. So this is like the miracle that makes possible singular value decomposition is that the eigenvalues, this is such an important thing that it needs to be like, written in a different page. So the singular values decomposition, one of the things that it says is that the eigenvalues of the matrix B transpose B is the same, are the same eigenvalues as B transpose. These two matrices have the same eigenvalues. But just know that you think that this is like a crazy thing because, like, for example, imagine that the matrix had been 10,000 times 2. Like, let's say you have a 10,000 times 2 matrix, right? So what is B transpose B? So this transposing changes the, that would change the size, right? Let's see what happens in this case. So the matrix B transpose would be 2 times 10,000, right? And the matrix B is 10,000 times 2. Oh, so this is just a 2 by 2 matrix. Huh. This is just a 2 by 2 matrix. And the other one is a 10,000 by 10,000 matrix. And what singular value decomposition says is that this 2 by 2 matrix, which can have only 2 eigenvalues, right, has the same eigenvalues as a 10,000 by 10,000 matrix. What that means is that the one with 10,000 times 10,000 has like a tons of repetitions, right? Like the same eigenvalue must appear multiple times. But that is like an insane thing because obviously I could have done something more extreme, like with 1,000,000 times 2 or whatever. You know what I mean? So in fact, that's how a lot of like singular value decomposition is very used, like in machine learning and other places, because basically what that gives you is kind of like the directions in which there's most variance in the data set, and then you kind of like project onto the space of eigenvectors with the largest singular values. And it has a lot of applications because of this particular fact. But kind of like the point of this, what I'm headed with this is that in the non-symmetric case, basically you define sigma max is defined as the maximum of the, of lambda 1. Well, let's see, the square root of lambda, okay, square root of lambda 1, square root of lambda 2, sorry, square root of lambda n, where here lambda 1, lambda 2, lambda n are the eigenvalues of one of these matrices, are the eigenvalues of B transpose B. The thing that why this works nicely is because if the matrix had been symmetric, if the matrix is symmetric, that just gives you B squared. So the eigenvalues of this matrix are like the squares of the eigenvalues of B, and when you take square roots, that kills the square root. So it kind of like coincides with the previous definition if the matrix is symmetric. because again, like here you would get B squared, if the matrix is symmetric. So it kind of all works nicely. Because the square root of lambda squared is after the value of lambda. So that's why it kind of reproduces the previous situation. And then you find, and in this case, then you would find what you can prove. I mean, that is harder. In this case, you can still prove. You can prove that the matrix norm is this sigma max. Okay, so for any matrix, whether it's rectangular or not, its matrix norm is always the largest of the singular values. So this is called like singular value. Well, this is a maximum singular value, so because it's the maximum of all of this. But it's always can be always computed in terms of an eigenvalue. It's just that you have to do this matrix P transpose P first. Okay. And again, like I'll tell you more about this next time, but this is really one of the more useful ideas of all like linear algebra, like these singular values. In fact, another insane thing you can do is that basically you can give the inverse almost any matrix, whether it's square or not, and that's called the pseudo inverse. So that also uses like the singular value decomposition. So essentially you can more or less invert almost any matrix. I mean, yeah, except a stupid case like where it's zero matrix. You can find kind of like the closest thing to the inverse of a matrix in any situation, and that's called the Penrose-Moore pseudo inverse, and that's another useful idea. So all those things are important. But let's finish this here, and then I can tell you the end of the story on Thursday. That way I can kind of like return the exams and all that stuff.